Mr. Buster, where the fuck you at? Can't scrap a lick, so I know you got your dick on hard from fucking your road dogs, the hood you threw up with niggas.
This is in the case where we have what's called irreducible quadratic q of x. Okay, so q of x. So quadratic, first of all, means you have some kind of x squared in there, right? Some power to this, some x to the second power, and then this would be, I guess, the general form of a quadratic is like this. So basically, when you can't reduce this to anything smaller, then it's called irreducible quadratic q of x. And q of x, as we remember, is on the bottom, right? So p of x we have on top, and then q of x is on the bottom. So when you have something like this, then the form is going to be, instead of having a plus a over something plus b over something plus c over something, what we're going to do now is have an ax plus b over whatever it is, whatever your irreducible quadratic function is, plus c plus, let's choose different letters, cx plus d over ax squared plus bx plus c plus, and then I'll just like dot dot dot, however many you have basically, and then like e of x, or ex plus f over the same thing. Okay, so again, this might look confusing, and I completely understand, but I'll write it in more simple terms on the next slide. Okay, so when we have a reducible q of x, that means that you can break it down into x minus some constant, right, times x minus another constant, times x minus a third constant, or something like that, okay? I'll just write the dot dot dot, so just for demonstrative purposes. When we have something like this, then the form is going to look like, our partial fractions will look like a over x minus the first thing, plus b over x minus the second thing, plus, and then all the way up to when you have c over the last thing that you're given on the bottom, okay? But when we have our irreducible one, irreducible q of x, which again is equal to something like ax squared, it has to have the squared, plus x, b of x, bx plus c, and then to some power, okay? So this could be squared, it could be cubed, etc. Anyways, so then our partial fractions are going to have the following form. They're going to be ax plus b. So the thing in this case, and I'll just keep writing as I'm talking, is that instead of having a constant on the top, as we did with the reducible one, so a, b, c, those are all constants, right? The capital letters. In the irreducible case, then we're going to have what are linear forms on the top, in the sense that these are all in the form like mx plus b, right? Because we have 1x, and then this is kind of like our slope. Yeah. Anyways, so that's the whole concept behind it. And then we're going to go all the way up to, let's see, until we have like e x plus f. And then, I'm sorry, hold on. This is a very important part. So this is like to the 1 power, the first thing that you write. And then the second, the denominator is raised to the second power, all the way up to bx plus c, until you raise it to the n power, which is however many they give you in the denominator. So we're going to do an example of this. So let's get started. So it's more understandable. So let's say they give us something like x minus 3 on top over x times x squared plus 1 dx. Okay, so here's a case where we actually, so this x here, that is technically reducible, okay? And then this thing in parentheses is irreducible. Okay, so technically it's allowed to have both reducible and irreducible existing in the same problem, okay? We're just going to have a combination of the two different types of fractions, all right? So what this is going to look like is, so this is going to get a constant on the top. The reducible is going to have like a on top, and irreducible is going to have a linear form, which means, well, I don't want to use the same coefficient, so we'll say like bx plus c. All right, so that's kind of like the form of the equation of a line. So that's what we're going to have on top for this, and then on top of the x, we're just going to have a simple a. So this is what it's going to look like, a over x, right, because this is reducible, plus, and we're going to have our linear form on top of the irreducible thing, okay? So that's the way you write it there, and our dx. Okay, so now what we're going to do is, so this is equal to the first thing that we had. Oh, actually, sorry, there is not a 3 there. I didn't want a 3. Okay, so ignore this 3, please. Okay, yeah, we're going to have that instead. So x, so this is equal to x over x times x squared plus 1 dx. Okay, so now we need to get our common denominators. So we're going to have, what I'd like to do for this, a quicker way that I think is you write the coefficient that you want. So we're looking at the a, and then what I do is I multiply it times all the other denominators except for the one it's over. So ignore the x, and then we'll multiply it by this thing, okay? So x squared plus 1, and we'll do the same with bx plus c. So bx plus c, and I like to write parentheses anyways just so I keep everything organized. So now we're looking here. So now we're going to multiply it times all the other denominators except for its own. So that would be the x, right? Okay, and then that's it. That's all for our fractions. And then we equal this, or equate this to the numerator of our given function. So this equals x, right? Because once we do all this, I mean, you can do the whole like fraction and then multiply times top and bottom, but you're going to get the same answer, okay? So once we simplify this, we're going to get ax squared plus a plus bx squared plus cx equals x. And this is like a 1x plus 0, right? Okay, so what we're going to do now, I'll move on to the next slide. So I'll rewrite this. We have our ax squared plus bx squared plus cx plus a equals, and we had 1x plus 0. And since we have x squareds on the left, we could add that in too. Technically there's 0 of them over here, so that helps as far as comparing coefficients. So we actually have an a plus b times x squared plus cx plus a, which is a constant, 0x squared plus 1x plus 0. Okay, so as we can compare, the first thing is the constants. So the only constant on the left is a, and the only constant on the right is 0. So a is going to have to equal 0. Wait, hold on. Yes, that's correct. Okay, so a equals 0, right? And then that makes it easy to figure out b, because a plus b should equal 0 as well when we're comparing the coefficients of the x squared terms, right? So if a equals 0, then b must also equal 0. So now we know b equals 0. And let's see, so c, now if we're comparing the coefficients of the x terms, c equals 1. Okay, so we have our three variables and our three constants, right? So now we're going to plug it back into our partial fractions. So what we have now, I'll go on to the next page. All right, so what we're going to have, well, here was the form, a over x plus bx plus c over x squared plus 1. That's a c, not an e. Dx. We found a equals 0, b equals 0, and c equals 1. Okay? So this actually turns out to be, what, 0 over x. So that's a 0. That goes away. So this term goes away. And then we have a 0 plugged in here, so that goes away as well. And a 1 in for the c. So we're going to have something that looks like this. Right? And let's see if you guys recognize this. If I put it in this form, I don't know, for some reason I recognize the integral of this more when I have the 1 in front of the x squared. But anyways, this is actually going to just be inverse tangent of x, right? And then plus c, of course, because we have an indefinite integral. Okay, so that just about does it for section 8.5. Okay, so I'll be talking to you on the homework videos if you watch.